322 WEFs in the summer of 2021, a heat dome stalled over the Pacific Northwest and killed over 1 billion shellfish on a single stretch of coastline in a matter of days. Subscribe, there's a new one every few days. This is White Space, settle in. In the summer of 2021, the ocean began to cook along a stretch of coastline from Northern California to the tip of Vancouver Island. Water temperatures climbed to levels scientists had never recorded in the historical record, not warmer than average, not unusually warm, simply unprecedented on beaches that had been ecologically stable for thousands of years. Something broke. Purple sea urchins baked alive in the shallows. Ochre sea stars dissolved into slime against the rocks. Mussels, which can survive briefly in air during low tide by closing their shells, couldn't close fast enough. The heat arrived too fast, lasted too long, and reached too deep into the intertidal zone for the normal mechanisms of survival to function. By the time researchers counted the bodies, they were measuring losses not in thousands but in billions. A single survey of exposed mussel beds on one stretch of shore in British Columbia estimated that more than 1 billion shellfish had died on that section of coastline alone. And this was not isolated. It stretched for hundreds of kilometers. What killed them was a meteorological feature that atmospheric scientists call a heat dome. The technical name is an omega block, named for its shape in pressure maps. A ridge of high pressure that stalls over a region and traps warm air beneath it, like a lid on a pot. The air compresses as it descends. Compression generates heat. That heat radiates downward into the sea surface and sideways into the land. And because the system is locked in place, there is no mechanism to flush it away. The heat simply accumulates. Oregon recorded its highest temperature ever measured. British Columbia matched it 2 days later. Lytton, a small town in the Canadian interior, reached 49.6 degrees Celsius before burning to the ground the following day in a wildfire almost certainly caused by the conditions the dome had created. Marine biologists who study intertidal ecosystems spent years documenting the aftermath. The mussels and barnacles that died were not simply cosmetic losses. They were the architecture. Mussel beds are habitat structures. They created the three-dimensional surface complexity that dozens of other species depend on, everything from whelks to shore crabs, to the seabirds that feed on them. When the beds die, the system beneath them collapses. Kelp forests attached to intertidal substrate lose their anchoring neighbors. Water that should be filtered by millions of bivalves circulates dirty. The sunlight that should penetrate to productive depths is blocked by suspended particles that nothing is cleaning. Recovery timelines based on earlier but less severe thermal events run to decades. And the question researchers are now confronting is whether recovery is the right framework at all, given that the conditions that produced this event are projected to repeat within years rather than generations. The ocean's relationship with heat is not passive. It absorbs roughly 90% of the excess energy trapped by greenhouse gases in Earth's atmosphere. This is why the sea surface temperature records that scientists maintain have been broken not once, but repeatedly in recent years, with each new record falling faster than the previous one. The ocean is a massive thermal buffer, but it has limits, and when those limits are approached, the effects can be sudden and non-linear. A species or an ecosystem that has adapted to a particular temperature range over thousands of years does not have a backup plan for 10 degrees above that range. It has no evolutionary memory of such conditions, it simply fails. What is happening to intertidal zones on the Pacific coast of North America is, in geological terms, happening instantaneously. The rate of change that is unfolding today would, measured against the deep timescale of Earth's history, appear as a vertical line on any graph. This matters because the planet has experienced dramatic warming events before. But those events unfolded over thousands of years, not decades. The difference between 1,000 years and a decade for a species or an ecosystem is the difference between adaptation and extinction. There are places on Earth where heat is not an anomaly, but a permanent condition. Places where the temperature does not rise because of a trapped weather system or a warming ocean. Places where it has always been extreme because of what lies beneath. The Yellowstone caldera in the American West sits above one of the largest volcanic hotspots on the planet. Beneath a landscape of grasslands and conifer forests and geothermal pools, a magma chamber stretches for roughly 90 kilometers and contains an estimated 300 cubic kilometers of partially molten rock. It is not the only such system on Earth. Iceland's entire island sits atop the mid-Atlantic ridge, the boundary between the Eurasian and North American tectonic plates, and is additionally underlain by a deep mantle plume. New Zealand's Taupo volcanic zone has erupted catastrophically more times in the past 100,000 years than most volcanic regions erupt in a million. And then there is Indonesia, which sits at the intersection of 3 major tectonic plates and has more active volcanoes than any other country on Earth. The 1815 eruption of Mount Tambora on the island of Sumbawa in what is now Indonesia produced the loudest sound in recorded human history and killed an estimated 70,000 people directly. But the event's most consequential effects were global and lasted for years. The eruption ejected somewhere between 150 and 180 cubic kilometers of material into the atmosphere. For scale, the entire volume of water in Lake Superior is roughly 12,000 cubic kilometers. The material Tambora launched into the stratosphere was ash and sulfur dioxide, and the sulfur dioxide combined with water vapor to form a reflective aerosol layer that encircled the planet. It reduced incoming solar radiation sufficiently to cause what 1816 became known as the year without a summer. In June of that year, frost killed crops in New England. Snow fell in Albany, New York in June. Switzerland experienced crop failures so severe that grain prices became unaffordable for ordinary people. In Ireland, famine killed tens of thousands. The potato harvest, on which much of the rural population depended, failed across multiple consecutive seasons in the wake of the volcanic disruption. In China, monsoon patterns shifted. In India, the late arrival of the monsoon created drought in regions that depended on it. The Bengal famine that followed contributed to the spread of cholera, which then traveled along trade routes and killed people from Asia to Europe. A single volcanic eruption, erupting for less than a week, reorganized the weather of the entire planet for years and caused suffering that cascaded through human populations for decades. The mechanism that connects these events is deceptively simple. When sulfur dioxide reaches the stratosphere, it forms sulfate aerosols. These aerosols scatter incoming sunlight back into space before it can warm the surface. The effect is relatively short-lived in geological terms, typically lasting 2 to 3 years before the aerosols settle out. But in human terms, 2 to 3 years of reduced harvests is a civilizational shock. The historical record shows that periods of intensive volcanism correlate with periods of political instability, empire collapse, and mass migration. The disruption does not announce itself as volcanic. To the people living through it, it simply looks like a run of terrible harvests and inexplicable cold. The question that volcanologists spend considerable effort on is whether systems like Yellowstone or Taupo or the Campifli caldera near Naples are approaching such events. The honest answer is that the monitoring tools available today are far more sensitive than anything that existed a generation ago. Satellite geodesy can measure ground deformation at millimeter precision. Seismic networks detect movements deep within magma chambers that would have been completely invisible in previous decades. Gas monitoring stations measure fluctuations in sulfur dioxide and carbon dioxide output in near real time. And what this monitoring has revealed is that large volcanic systems breathe. They expand and contract. They experience episodes of elevated seismicity. They occasionally deform their surfaces upward by meters over years, then subside again. This rhythmic activity does not necessarily indicate an impending eruption. It reflects the complex dynamics of a thermal system that has been operating for hundreds of thousands of years. But it also means that the question of prediction remains one of the deepest unsolved problems in Earth science. To understand why volcanic systems are so difficult to predict, it helps to understand what lies beneath them, and to understand that, it helps to go deeper, much deeper. There is a hole in the Kola Peninsula in the far northwest of Russia that was drilled between 1970 and 1994 by Soviet scientists attempting to answer a basic question. What is the continental crust actually made of? And does its composition match theoretical predictions? The hole is called the Kola Superdeep Borehole, and at its maximum depth of 12,262 meters, it remains the deepest artificial structure ever created by human hands. It is not especially wide, roughly 23 centimeters in diameter, and from above it looks like nothing more than a capped pipe. But what the drilling retrieved fundamentally changed how geologists understand the planet. The first surprise was temperature models predicted that rock temperatures would follow a predictable gradient. What the drill encountered was dramatically higher heat than expected. At 6 kilometers depth, temperatures exceeded 100 degrees Celsius. At 12 kilometers, they approached 300 degrees. This mattered because it set an effective limit on drilling. Rock at those temperatures behaves plastically. It flows slowly, and the drill hole cannot be maintained in material that closes around it as it cuts through. This is part of why no drilling program has ever penetrated more than a fraction of the way through the crust, let alone reach the mantle below. The second surprise was structural. Geologists had predicted, based on seismic data, that the transition from granite to basalt at that depth would be a change in rock type. What they found was not a change in rock type, but a change in rock condition. The granite at depth had been fractured and altered by heat and pressure to the point that it transmitted seismic waves as though it were basalt. The boundary that seismologists had been measuring for decades reflected not a chemical change, but a physical transformation. The third surprise, and arguably the most remarkable, was biological. At approximately 7 kilometers depth, the Kola borehole intersected rock formations containing microscopic fossils, ancient single-celled organisms preserved in thin films of mineralized carbon encapsulated in rock that was 2 billion years old. Not only were these among the oldest biological specimens ever recovered, they suggested that life had been far more widespread and far more deeply embedded in Earth's crust at an early stage than anyone had previously imagined. This has since become one of the driving questions of what scientists call deep biosphere research. How far down does life go? The technical answer at present is deeper than anyone initially thought possible. Microorganisms have been recovered from boreholes in South Africa at depths exceeding 3 kilometers, living in complete darkness, in water that has not been in contact with the surface for millions of years, in conditions of extreme heat and pressure, surviving on chemical energy rather than sunlight. These organisms, some of them ancient lineages of bacteria and archaea, exist so slowly and reproduce so infrequently by surface standards that they might be better characterized as geological features than as creatures. Some of them, based on carbon dating of the organic matter they consume, appear to have been metabolically active for tens of thousands of years without reproducing. The total mass of subsurface life on Earth is, by some estimates, comparable to the total mass of surface life. The biosphere does not stop at the ground. It extends downward through kilometers of rock, through chemical gradients and thermal zones, into a world that operates on time scales and by processes that have almost nothing in common with the world above. This changes the way astrobiologists think about the search for life elsewhere. A planet whose surface is frozen or irradiated or chemically hostile is not automatically a dead planet. What matters is whether it has liquid water, chemical gradients, and sufficient geological activity to maintain the conditions that subsurface life requires. Mars, which almost certainly had surface water billions of years ago and which still shows signs of residual geothermal activity, may host microbial communities beneath its surface today. Below the crust lies the mantle, a layer of rock roughly 2,900 kilometers thick that makes up approximately 84% of Earth's total volume. The mantle is not liquid, though it is sometimes described as molten. It is solid rock, but rock subjected to such extreme pressure and temperature that it deforms plastically over geological time. A piece of mantle rock observed in a laboratory over the course of a human lifetime would appear completely rigid. Observed over 1 million years, it would flow. This slow movement of mantle material drives the tectonic system that reshapes Earth's surface, builds mountain ranges, opens ocean basins, and delivers volcanic magma to the surface through a variety of pathways. Geologists have learned most of what they know about the mantle's composition from fragments brought to the surface involuntarily. Diamonds form at depths of at least 150 kilometers under conditions of extreme pressure, and they occasionally arrive at the surface enclosed within a type of volcanic rock called kimberlite, which erupts explosively and carries material from the deep mantle directly upward. Inside some diamonds, researchers have found inclusions, tiny trapped pockets of material that preserve the chemical conditions of the deep mantle at the moment the diamond crystallized. These inclusions have revealed, among other things, that the mantle transition zone, a layer between roughly 410 and 660 kilometers depth, contains significant quantities of water stored within the crystal structures of high-pressure minerals. The amount of water present in this zone may be comparable to the volume of all the world's oceans. It exists not as liquid, but as hydroxyl groups bonded into mineral lattices, but it is chemically water nonetheless, and its presence has significant implications for how the mantle flows and how volcanic systems above it behave. At the center of the planet, at a depth of roughly 6,370 kilometers from the surface, lies the inner core. It is a sphere of solid iron, approximately 2,400 kilometers across, surrounded by a liquid outer core of iron and nickel, roughly 2,200 kilometers thick. The temperature at the inner core boundary approaches 6,000 degrees Celsius, roughly the same as the surface of the Sun. The pressure exceeds 3 million atmospheres. Under these conditions, iron adopts a crystalline structure, unlike anything achievable in a surface laboratory. The inner core rotates. This has been known for some time, but recent seismic studies using earthquake data accumulated over several decades have suggested something stranger. The inner core's rotation rate is not constant. It appears to oscillate, speeding up and slowing down over periods of decades. In 2023, a study published in Nature Geoscience proposed that the inner core may have reversed its rotation direction relative to the mantle within the past few years. The implications of this, if confirmed, are not yet fully understood. The inner core's rotation is connected to the dynamics of the liquid outer core, which in turn generates Earth's magnetic field. Changes in inner core behavior may produce slow variations in field intensity and geometry variations that, on very long time scales, contribute to the magnetic pole migrations and occasional field reversals that are preserved in the magnetic signatures of ancient volcanic rock. Venus has a similar mass to Earth, but no active dynamo, and its atmosphere is a crushing 90 atmospheres of carbon dioxide. Earth's habitability is in part a consequence of its molten outer core, its rotation rate, and the specific geometry of the flow patterns within that core. The inner core is not a passive artifact of planetary cooling. It is part of a living thermal engine that maintains the conditions for life on the surface. The surface itself has a memory. And sometimes that memory contains things we do not expect in the language of geology. The word for an identifiable layer in the rock record is a stratum. Strata accumulate over time, compressing into stone under the weight of everything deposited above them. They contain fossils, chemical signatures, isotope ratios, and other markers that allow geologists to reconstruct the environmental conditions that existed when those layers were being formed. The geological record is a kind of archive, imperfect and discontinuous, but readable by those who know the language. In 2019, two researchers, Adam Frank of the University of Rochester and Gavin Schmidt of the NASA Goddard Institute, published a paper asking a question that sounds almost absurd on its surface. Would it be possible, using only the geological record, to detect whether an industrial civilization had existed on Earth tens of millions of years ago? They called these Silurian hypothesis, borrowing the name from a science fiction species but applying it to a serious scientific inquiry. The answer they arrived at was possibly, but with great difficulty, and we would likely miss most of the evidence. The reasoning goes like this. Industrial civilizations alter the chemistry of the atmosphere, the isotopic composition of carbon in sedimentary deposits, the concentration of certain synthetic chemical compounds, and the pattern of species extinctions. Modern human civilization has done all of these things, and its signature is already becoming visible in the geological record in ways that will likely be detectable millions of years from now. But the signature is thin. Industrial civilization has existed for roughly 300 years. In the context of geological time, 300 years is essentially a point. The layers that will represent our era will be perhaps a few centimeters thick in the rock record of the distant future. A civilization that existed 50 million years ago and lasted for a similar period would leave a signature of comparable thinness, buried under kilometers of subsequent deposition, overprinted by later events and accessible, if at all only in the rare geological settings where 50 million-year-old sedimentary sequences are exposed at the surface. There is one known event in the geological record that resembles, in some ways, what a vanished industrial civilization might have produced. Approximately 56 million years ago, at the boundary between the Paleocene and Eocene epochs, global temperatures rose by 5 to 8 degrees Celsius over a period estimated at between 20,000 and 200,000 years, then gradually recovered over the following 200,000 years or so. This event is known as the Paleocene-Eocene thermal maximum, and it is associated with a massive injection of carbon into the atmosphere. The isotopic signature of this carbon indicates it came from a reservoir that had been isolated from the surface carbon cycle for an extended period, potentially from the destabilization of methane hydrates on the ocean floor, or from a large volcanic igneous province, or from some combination of geological factors. The PETM caused mass extinction among deep-sea foraminifera and drove major reorganizations of terrestrial ecosystems. It was by any measure a catastrophic event. It was not, as far as anyone can determine, caused by an industrial civilization, but the point that Frank and Schmidt were making is subtler than that. They were asking whether the tools of geology are sensitive enough to rule out such an explanation with certainty. And the answer, honestly evaluated, is that they are not. The carbon isotope anomaly at the PETM has a shape and duration that is consistent with natural causes. But if a technological civilization had released comparable quantities of carbon over a comparable period, the geological signature might look essentially identical to a natural event. The sedimentary record simply does not have the resolution to distinguish them. This raises a related question that is more unsettling. We know that anatomically, modern humans appeared roughly 300,000 years ago. We know that complex, urban, literate civilizations appeared only within the last 10,000 years. We know that industrial civilization emerged only within the last 300. In the 4.5 billion years of Earth's history, complex life has existed for something like 550 million years. In all of that time, Is it conceivable that another lineage reached something approaching technological capability, altered the environment significantly, and then went extinct, leaving no trace that would be recognizable to us now? The question is not answered by the Silurian hypothesis. The hypothesis does not assert that this happened. It only asks whether we would know if it had, and the geological record, for all its power, cannot give a confident answer. What this reveals, among other things, is how recent and fragile our own footprint actually is. The civilization that operates global communication networks, fills low Earth orbit with satellites, and debates whether its industrial activity is transforming the climate is, geologically speaking, a vanishingly brief phenomenon. Whether it becomes something more persistent, or whether it joins the silence of whatever may have come before, depends on choices being made right now, in the human present, on a timescale that geology will barely register. The ground beneath every city, every field, every ocean floor is not still. It never has been. On February 6, 2023, 2 major earthquakes struck southeastern Turkey in quick succession. The first, with a magnitude of 7.8, occurred at 4:17 in the morning local time, when most people in the region were asleep. The second, of magnitude 7.7, struck approximately 9 hours later. Together, they killed more than 56,000 people across Turkey and Syria, making the event one of the deadliest natural disasters in the recorded history of either country. The rupture zone extended for hundreds of kilometers along the East Anatolian Fault, one of the major tectonic boundaries where the Arabian Plate slides against the Eurasian and Anatolian plates. The fault had been accumulating stress for centuries. In minutes, it released it. To understand what happened in Turkey in February 2023 requires going back to the most basic mechanics of how solid rock fails. Earth's outer shell, the lithosphere, is not a continuous surface. It is divided into approximately 15 major tectonic plates and several dozen smaller ones. These plates move continuously, driven by convective currents in the mantle below and by gravitational forces at subduction zones, where denser ocean plate descends beneath lighter continental material. The plates move slowly, typically between 1 and 10 centimeters per year, rates comparable to the growth of a human fingernail. But the cumulative effects of this movement over geological time are enormous. The Himalayas have been built by the ongoing collision of the Indian and Eurasian plates. The Atlantic Ocean has been widening for 180 million years. The Pacific Ocean is being progressively consumed along its margins. At the boundaries between plates, the interactions take 3 basic forms. At divergent boundaries, plates move apart, and new crust forms from volcanic material welling up from below. The mid-Atlantic ridge is a divergent boundary, and it is why Iceland, which sits on top of it, is geologically among the most active places on Earth. At convergent boundaries, plates collide. Where both plates carry continental crust, they buckle upward and form mountain ranges. Where ocean crust meets continental crust, the denser ocean plate descends, melts at depth, and generates volcanic arcs above the subduction zone. Japan, the Cascades of the Pacific Northwest, the Andes of South America, all are products of subduction. At transform boundaries, plates slide horizontally past each other, neither creating nor destroying crust. The San Andreas Fault in California is a transform boundary. So is the East Anatolian Fault that ruptured in Turkey. The reason transform faults produce such destructive earthquakes is rooted in the physics of friction as 2 plates grind past each other. The irregularities along the fault surface lock. The rock on either side of the fault continues to be pushed and pulled by the forces driving plate motion. But the locked section cannot move. Stress accumulates. It accumulates over decades, over centuries, sometimes over millennia, stored as elastic strain energy in the surrounding rock. When the stress finally exceeds the frictional strength of the locked section, it fails catastrophically. The two sides of the fault snap past each other, sometimes by several meters in the span of seconds, and the energy that had been stored in the rock radiates outward as seismic waves. Seismologists measure earthquakes using a logarithmic scale. On the moment magnitude scale now used by most agencies, an increase of 1 unit represents approximately 32 times more energy released. A magnitude 7.8 earthquake releases roughly 1,000 times more energy than a magnitude 6.8 and roughly 30,000 times more than the magnitude 5.8. The 2023 Turkey earthquake released an amount of energy roughly equivalent to 200 or 300 atomic bombs of the Hiroshima scale, all concentrated along a fault rupture that extended for over 300 kilometers. The reason some earthquakes are devastating and others of comparable magnitude are not comes down to several factors: depth of the rupture, distance of population centers from the fault, local soil conditions, and the quality of building construction. Earthquakes do not kill people directly. In most cases, they kill people by causing buildings to collapse. An earthquake that occurs beneath an ocean, far from any coast, may produce no casualties at all. The same earthquake beneath a city built on loose, water-saturated sediment with inadequate building standards can kill tens of thousands. This is why earthquake risk is as much a social and economic problem as a geological one. The seismic waves produced by earthquakes are the primary tool geologists have for imaging Earth's interior. Different types of seismic waves, called primary waves and secondary waves, travel through the planet at different speeds and behave differently when they encounter boundaries between materials of different density or physical state. Primary waves, which are compressional, can travel through both solid and liquid rock. Secondary waves, which are shear waves, cannot travel through liquid at all. By analyzing the arrival times of these waves at seismographs distributed around the globe, scientists have mapped the internal structure of the planet with remarkable precision, identifying the boundaries between the crust, the various layers of the mantle, the liquid outer core, and the solid inner core. But seismology has revealed something else, something that has puzzled researchers since it was first recorded in 1962 by a geologist named Jack Oliver at the Lamont Doherty Geological Observatory. Every 26 seconds, Earth pulses, a seismic signal of extraordinary regularity, repeating like a heartbeat, detectable at monitoring stations around the world. Oliver was the first to notice it, and he identified its source as somewhere in the southern Atlantic. He called it a microseism, a small but persistent seismic signal with no obvious natural cause. For decades, the pulse attracted occasional scientific attention, but no definitive explanation. The question was whether it was geological, arising from some rhythmic process in Earth's interior, or physical, generated by some repetitive interaction between the ocean and the seafloor. In 2005, a graduate student named Greg Bachievsky used new digital seismic records to re-examine the source location with more precision. The analysis pointed to a specific area, the Bight of Bonny, an embayment in the Gulf of Guinea off the coast of West Africa. This placed the source near the volcanic island of Toney, which sits on a hotspot, a plume of hot mantle material punching through the ocean floor. Two competing explanations emerged. One held that the pulse was generated by ocean waves interacting with the seafloor bathymetry, specifically with the shape of the continental shelf in the region. Ocean swells of the right period interacting with a seafloor that has the right geometry could in principle generate a resonant seismic signal. The other explanation pointed to the volcanic system beneath São Tomé, suggesting that periodic pressure fluctuations in the magmatic system were producing the repeating signal. Both explanations remain on the table. Neither has been definitively ruled out. What the 26-second pulse illustrates is that Earth is not a passive substrate. It is a dynamic system with its own rhythms, some of them poorly understood, generated by processes that operate at the intersection of geological, oceanographic, and atmospheric physics. The planet has a pulse. It breathes through tectonic rifts and volcanic vents. It redistributes heat over timescales ranging from the daily to the geological, and much of what it is doing remains even now beyond our ability to fully decode. The atmosphere above this dynamic surface is no more stable than the rock beneath it. Climate is not weather. Weather is what is happening in the atmosphere over the next few days or weeks. Climate is the long-term statistical behavior of the atmosphere-ocean-land system, the envelope within which weather occurs. Earth's climate system is driven by one primary energy source, the sun, and is shaped by the way that energy is distributed, absorbed, reflected, and re-emitted by the atmosphere, the oceans, the land surface, and the ice. Of all the large-scale climate phenomena that affect human societies, few are as consequential or as regularly misunderstood as the coupled ocean-atmosphere system known as El Niño Southern Oscillation. The name encompasses two related patterns. El Niño refers to the periodic warming of sea surface temperatures in the central and eastern tropical Pacific, which occurs when the trade winds that normally push warm surface water westward weaken or even reverse. La Niña refers to the opposite condition, an anomalous cooling of the same region, when the trade winds intensify and push warm water further west, allowing cold water to upwell along the South American coast. Together, these two phases constitute a natural oscillation of the coupled ocean-atmosphere system, cycling over periods of roughly 2 to 7 years. The physical mechanism that drives this oscillation is a feedback loop. Under normal conditions, the trade winds blow from east to west across the tropical Pacific. They pile warm surface water up against the coasts of Australia and New Guinea, where it is typically several degrees warmer and roughly half a meter higher than water at the same latitude on the South American side. This warm water drives atmospheric convection, generating the rainfall that sustains tropical ecosystems across the Western Pacific. The cold, nutrient-rich water that upwells off South America feeds one of the world's most productive fisheries, the Humboldt Current System, which supports anchovy populations of enormous commercial importance. When El Niño begins, the trade winds weaken. The water they had been piling up against the Western Pacific begins to slosh back eastward. As it does, it suppresses the upwelling of South America. The thermocline, the boundary between warm surface water and cold, deep water drops, where it was normally at perhaps 50 meters depth, it may drop to 150 meters or more. The cold, nutrient-rich water can no longer reach the surface. The fisheries collapse. The rain that was falling over Indonesia and Papua New Guinea migrates eastward toward the Pacific coast of South America, bringing floods to areas that are normally dry and drought to areas that normally receive reliable monsoon rains. Australia, Southeast Asia, and parts of sub-Saharan Africa tend to dry out during El Niño events. Parts of California and the American Gulf Coast tend to get wetter. The disruption is hemispheric in scale. The strongest El Niño events in the modern instrumental record, those of 1982, 83, and 1997, 98, each caused billions of dollars in economic damage and were associated with thousands of deaths from floods, droughts, wildfires, and storm systems whose patterns had been reorganized by the anomalous Pacific temperatures. The 2015-16 event was comparable in intensity and produced similarly wide-ranging effects. Coral bleaching, driven by the anomalously warm water, killed large areas of reef across the tropical Pacific, including significant portions of the Great Barrier Reef of northeastern Australia. The interaction between El Niño and anthropogenic climate change is one of the more complex scientific questions in contemporary climatology. Global warming does not simply make El Niño stronger or more frequent in any straightforward way. What it appears to do based on observational data and climate models is raise the baseline ocean temperature on top of which El Niño events occur. This means that an El Niño of the same intensity as a historical event will produce higher sea surface temperatures in absolute terms, with correspondingly stronger effects on coral bleaching, species distributions, and rainfall patterns. The extreme events of the future will be built on a warmer foundation, making them more consequential even if their oscillatory intensity is not greater. Beyond El Niño, the climate system contains numerous other large-scale patterns whose behavior is not fully understood. The Atlantic meridional overturning circulation, which carries warm surface water northward from the tropics and returns cold deep water southward, has been measured to be weaker now than at any point in the past 1,000 years based on proxy records. If it were to slow substantially or collapse, the consequences for the climate of Europe and North America would be severe. Though the direction and magnitude of the resulting changes is still debated, the Indian Ocean Dipole, the stratospheric polar vortex, the Pacific decadal oscillation, all of these are climate modes whose rhythms interact with each other and with the anthropogenic forcing that is now overlaid on the natural system. Understanding how they will collectively evolve is among the most important and most difficult scientific problems of the century. There are also regions of Earth where the interaction between atmosphere, ocean, and geology has produced something that has defied systematic explanation for decades. The Sargasso Sea occupies a roughly 4 million square kilometer region of the North Atlantic, bounded not by any continental landmass, but by ocean currents. The Gulf Stream to the west, the North Atlantic Current to the north, the Canary Current to the east, and the North Atlantic Equatorial Current to the south. It is the only sea in the world defined entirely by water boundaries. It takes its name from the sargassum seaweed that floats in vast mats across its surface, creating a floating ecosystem unlike any other on Earth. Eels from rivers across Europe and eastern North America migrate here to reproduce, traveling thousands of miles to a specific patch of ocean before dying. The larvae drift back on ocean currents to the freshwater systems from which their parents came, following cues that are not yet fully understood. Within the western part of the Sargasso Sea lies a region that has been embedded in popular culture for half a century as a source of mystery, fear, and speculation. The area is commonly described as extending from the tip of Florida to the island of Bermuda to Puerto Rico, enclosing roughly 1 million square kilometers of Atlantic Ocean. Mariners, military personnel, and commercial operators have been noting unusual incidents in this region for more than a century. Ships have been found abandoned, their crews missing aircraft have disappeared without sending distress signals. Search operations have recovered no wreckage, and the disappearances have accumulated into a pattern that, at some point in the 1960s and 70s, began to acquire the weight of legend. The historical record of maritime disasters in this part of the Atlantic is real. In 1918, the USS Cyclops, a US Navy collier over 160 meters in length and carrying 306 crew and passengers, vanished between Barbados and Chesapeake Bay without sending any radio distress call. No wreckage was ever found. In 1945, 5 Grumman TBF Avenger torpedo bombers on a routine training flight from the Naval Air Station at Fort Lauderdale, Florida, became disoriented, lost radio contact, and disappeared over the Atlantic. The flight leader's voice, preserved in radio recordings from the incident, described conditions that experienced pilots found inexplicable: instruments malfunctioning, the ocean looking wrong, the sun invisible despite clear weather conditions at departure. A flying boat sent to search for them also disappeared within 30 minutes of takeoff. 14 aviators and the 5 aircraft of Flight 19 were never found. The flying boat and its 13 crew were never found. Nothing was ever recovered. These events are facts. The question is how to interpret them, and this is where careful analysis diverges sharply from mythology. The region of ocean between Florida, Bermuda, and Puerto Rico is one of the most heavily trafficked in the world. Hundreds of commercial vessels and thousands of private boats transit it every year. Aircraft cross it continuously. The US Coast Guard, which maintains detailed records of incidents at sea, does not categorize this region as statistically more dangerous than comparable areas of open ocean. Lloyd's of London, the insurance market that has priced maritime risk for centuries, does not charge higher premiums for vessels transiting this area. Insurance markets tend to price risk accurately because they lose money when they get it wrong. Their assessment is that there is no anomalous danger here. What the region does have is the conditions for genuine maritime hazards that are not supernatural but are genuinely serious. The Gulf Stream runs along its western boundary. The Gulf Stream is a river of warm, fast-moving water within the ocean, 1 to 2 kilometers deep, sometimes 80 kilometers wide, flowing at speeds of up to 9 kilometers per hour. Any debris from a sinking vessel in this region will be swept rapidly away from the accident site, making post-event searches almost futile. A ship that sank in the Gulf Stream in 1918 might have dispersed its wreckage across thousands of kilometers in the weeks following the sinking. Finding no wreckage proves nothing about the cause of the sinking. The region also experiences some of the most severe weather in the North Atlantic. Tropical cyclones trek northward along the Gulf Stream corridor regularly. Waterspouts are common. Sudden, severe thunderstorms can develop with minimal warning in the warm, humid air over the Gulf Stream. The sea floor beneath the region is among the most geologically complex in the Atlantic Basin, with water depths ranging from shallow reef systems in the Bahamas to the Puerto Rico Trench, which at over 8,000 meters is the deepest point in the Atlantic. A vessel that sank in the trench would be effectively irretrievable with any technology available in the 20th century, and would remain difficult to locate even today. One hypothesis that has attracted legitimate scientific attention involves methane hydrates. These are cage-like structures of water ice that trap methane molecules within them, forming a solid on the ocean floor at the low temperatures and high pressures found in deep water. The Gulf of Mexico and the Atlantic margin of the southeastern United States contain significant methane hydrate deposits. If these hydrates destabilize, they can release large amounts of methane gas, which bubbles up through the water column in what is sometimes called a gas eruption. Laboratory experiments and the limited number of field observations suggest that sufficient methane release can significantly reduce the density of seawater, potentially causing a vessel to lose buoyancy suddenly and without warning. The mathematics of this is straightforward. A vessel floats because its density is less than the surrounding water. Reduce the water's density enough, and the vessel sinks regardless of its construction or the skill of its crew. Whether methane hydrate destabilization has actually caused any documented sinkings in the Atlantic, including in the region commonly called the Bermuda Triangle, remains unproven. There is no confirmed instance where this mechanism has been identified as a cause of a maritime disaster anywhere in the world, but the mechanism is physically plausible and the deposits that would be required exist in the region. It is an hypothesis that the evidence neither confirms nor excludes. For aircraft, the problem is different. The Avenger torpedo bombers of Flight 19 were lost in 1945, before the era of satellite navigation, radar coverage of the open ocean, or modern meteorological forecasting. The navigational instruments of that period were sensitive to magnetic disturbances in ways that modern systems, which rely on satellite positioning, are not. The flight leader's description of his compass behavior as anomalous is consistent with any number of phenomena, including flying into an intense electrical storm, which can affect magnetic instruments.
The detail that the ocean looked strange may reflect that they had become disoriented about their heading and were viewing a familiar body of water from an unfamiliar angle. Spatial disorientation in instrument meteorological conditions is a leading cause of aircraft accidents, even today, among pilots flying aircraft far more sophisticated than a 1945 torpedo bomber. The most likely explanation for the accumulated incidents attributed to the Bermuda Triangle is not a single mysterious force, but the ordinary operation of maritime hazard in a busy, dangerous, weather-prone region of open ocean, combined with the conditions that make finding lost vessels in deep, fast-moving water extremely difficult, and amplified by the human tendency to see patterns and assign meaning where statistics and geography provide the actual explanation, and yet the ocean keeps its secrets. Not because it conceals supernatural forces, but because it is vast, deep, and indifferent. The Titanic, one of the most famous shipwrecks in history, sank in 1912 in the North Atlantic and was not found until 1985, despite being one of the most searched for wrecks in the world. Its location, when finally discovered, was more than 1,000 meters from where the best estimates had placed it. Scale, depth, and current conspire against recovery in ways that can make a genuine tragedy look like a mystery. The planet on which all of these events occur, all the heat domes and volcanic eruptions, all the earthquakes and seismic pulses, all the climate oscillations and ocean mysteries, is 4.5 billion years old. In those 4.5 billion years, it has been struck by objects large enough to melt its surface, frozen to the point where ice reached the equator at least twice, warmed until crocodiles lived in Arctic latitudes, reorganized its continental arrangements repeatedly through the slow churn of plate tectonics, and witnessed the origin and extinction of the vast majority of species that have ever lived. The civilization that now monitors it with satellites and seismographs and ocean buoys has existed for a geological instant. The capacity to study this planet, to read its rock layers, to probe its interior with seismic waves, to track the temperature of its oceans from orbit, to model the behavior of its atmosphere decades into the future, is something genuinely new in Earth's history. It represents the first time that any organism on this planet has developed the ability to understand the system it lives within. That understanding is incomplete. There are categories of phenomena, from the 26-second seismic pulse to the precise dynamics of the mantle transition zone to the long-term behavior of the magnetic field, that remain genuinely open scientific questions. But the incompleteness of our understanding is not the same as mystery in the popular sense. It does not imply hidden forces or unknowable depths. It implies that the scientific project of understanding this planet is unfinished, and that the tools and observations being accumulated today will eventually resolve questions that currently have no answer. The history of Earth science is a history of phenomena that once seemed inexplicable, from the drift of continents to the existence of deep-sea hydrothermal vents, that became explicable through the accumulation of evidence and the development of better instruments and models. We live on the surface of a planet that is thermally active from its radioactive core to its sunlit outer atmosphere, geologically restless along hundreds of thousands of kilometers of tectonic boundaries, biologically inhabited from its upper atmosphere to kilometers into its own crust, and chemically coupled to the sun through an atmospheric system of staggering complexity. It is not a backdrop. It is a participant in everything that occurs upon it. To understand even a fraction of what this planet is doing is to recognize both how much we know and how much remains. The rock beneath your feet is moving, the mantle below the rock is flowing, the core at the center of everything is rotating and generating the field that makes our lives possible. The ocean is redistributing heat across the hemisphere. The atmosphere is cycling carbon through processes that are now being altered faster than they have been since the impacts that ended the reign of the non-avian dinosaurs. Earth is not a mystery, it is a system in process, and we briefly and remarkably are its witnesses.